Okay, so here's what we've got in terms of like the next kind of week. So we figured out like the physics toolkit, how to graph stuff, the units, how to do dimensional analysis. And we rolled that into velocity and how we calculate that and what it means and vector quantities and all that good stuff. And so now we're on to the acceleration unit. So you have to learn velocity, because if you don't know what velocity is, you can't learn what acceleration is, because acceleration is a rate of change in your velocity. So if you don't know what velocity is, you can't tell if it's changing. So that's why you kind of have to sequence it. And then from there, we're going to roll that into the next unit on forces, and that's force equals mass times acceleration, F equals ma. So that's where we kind of go in the sequence. You got to figure out velocity, then you want to change velocity, which is acceleration, then you can do acceleration, then you can calculate forces. So if you really want to plan ahead, okay, and some people really like to plan ahead, this next unit on acceleration is kind of a dichotomy. It's going to be the most equation-intense unit that we've had, but it's also going to be the shortest unit in terms of getting ready for a test. So the test over acceleration is going to be a week from tomorrow, okay? Because there's 4 equations, and we'll start to learn those even today. And so that acceleration test will be the first like kind of really big test in this class, okay? So if you're a planner, you go, oh, I want to, plan your calendar. So a week from tomorrow will be the first really big test over acceleration. So funny ones, oh, I didn't know you were having that test. Yes, you did. Okay. So with the acceleration unit, most of the time you like kind of learn the theory and then you do the lab. So this one I kind of reverse it. We're going to start with the lab, and that's going to be kind of an introduction to this whole idea of acceleration. And then that's going to roll us into the actual equations itself. So the lab itself is fairly simple. What you're going to do is you're going to take a track like this, okay? And we'll use these a lot. And these have like a measuring tape glued on the end of it. So you're going to go from 0, and these are centimeters, okay? It's like 10 centimeters, 20, whatever. And it goes all the way up to 122. So you're going to put it on a table, like so. And you have a cart, okay? And all you have to do is kind of give it a push, okay? And it's going to go up, and then it's going to come back down. Now, obviously, don't try and do it like this. It's not going to work very well. So make sure you got the wheel sides down, even though I don't explicitly tell you in the instructions, put the wheels down. So you go from here, doink, back to here. Now, a couple of things. We're not including the push, okay? The push is not part of the lab. So we're going to start this thing as soon as it leaves your hand until it gets back to that same point, okay? So don't include the push. Anything going up the ramp is going to be positive. Velocity, acceleration, displacement. Anything going up is positive. Anything going down is going to be negative. So make sure that you put the 0 mark at the bottom. Now, the other thing that your group is going to have to decide is, what do you want to measure from? You either decide to measure off the back of the cart or the front of the cart. I don't care which one, because what you have to keep track of is where the cart is when it leaves your hand. You have to keep track of where it is at its highest point, and then when it gets back to that point in terms of timing. Okay? So you don't want somebody measuring where the back of the cart is when you let go of it, and then somebody watching the front of the cart when it gets up here. Because then your measurement's going to be off by the length of the cart. Okay? There's no right or wrong answer. I don't care. Just make sure everybody in the group decides, let's pick a coin or flip a coin. Are we going off the back or are we going off the front? Don't care. Just make sure everybody's together. So you need to keep track of the entire time as well. I'd have at least 2 people timing that so you can make sure your times are precise and relatively close to each other. So you're going to have like Allison, she's going to be watching and she's going to be timing. You might have Katie watching where it goes up here, okay, so you got to have that number. And then have somebody else timing the entire time. So what I don't want one person timing it going up and the other person timing it going down. You want to time it from start to finish when it gets back to that point, but don't include the push. Okay, so based upon this observation of what you see, what are some things that you can tell me that the cart does?
Changes direction.
You have a change in direction, okay? So, if it's going to change direction, what three things have to happen?
Slow, stop, start.
Now, do all those things happen?
No.
They don't?
No.
Okay? They do, right? Because on the way up, what's it doing? Slowing down. Does it stop at the top?
Yes.
It's going to speed back up, right? Okay, so this is like the quintessential example. So Galileo was actually the first one to use this technique of inclined planes. So if you think about it, it's like you're watching the effects of gravity, but you're watching them in slow motion. So it's almost like being on the moon, because you see things slow down, and then you see them speed up, but it takes place over a relatively long amount of time. I can throw this up in the air, but that's a pretty quick change. If I use an inclined plane like Galileo did, then I can still observe the effects of gravity. I can just watch them like in slow motion. All right, so you said we're going to change direction, which is spot on. Now, at the bottom, here's your ramp. You're going to give this thing a push, right? And it's going to have some initial velocity. Now, one of the things we're going to do a lot is I'm going to ask you to draw what we call motion diagrams, where you draw velocity vectors and you draw acceleration vectors. So and you're going to do this on the lab. So I'm going to say, okay, here's this initial velocity vector, v1. So as this thing goes up the ramp, one of three things can happen. The velocity vector can point up the ramp and get bigger because it's speeding up. Okay, that's an option. The velocity vector can just maintain the exact same size, not speed up or slow down, just move at a constant velocity. And that's actually what Mother Nature prefers. So we'll talk more about Newton's three laws of motion, but Mother Nature lays a prima donna. Basically says, hey, if you have a velocity vector, chill out. You've got it. I don't want to change your velocity vector. But if you see that velocity vector changing, whether getting bigger, getting smaller, or changing direction, the only way that's going to happen is a force, because Mother Nature isn't going to do that on her own. So if you see something speeding up, slowing down, or changing direction, there has to be an external force acting on that object. So it can get bigger, it can stay the same size, or it can become smaller. So Zoe, what's it going to do going up the ramp? What's going to happen to that velocity vector? Bigger, smaller, stay the same? Smaller. So you come in here and you draw maybe V2, something like this, and then V3, even something smaller than like that. Okay? Now when you draw these, if you want me to think that they're getting smaller, you draw them so I can clearly see them getting smaller. If you think they're going to get bigger, you draw them getting bigger. These eyes are 55 years old. They've seen a lot. I am not going to guess how you want your vectors to change. Okay? If you want to get them bigger, you draw them bigger. Smaller, smaller. If you want them to be the exact same length, you draw them the exact same length. Okay. So, Zoe's right. It's going up the hill, these vectors are going to get bigger. So based upon that, hit, is it accelerating? Yeah, how do you know? Yeah, we're changing our velocity vectors. If the velocity vectors were staying the same, there would be no acceleration. Okay? So here's the next question, Kevin. Since it's accelerating, are my acceleration vectors going to point down the ramp or up the ramp? What'd you say? They are. Perfect. Why? That's slowing down, right? So if something's slowing down, what do you know about velocity and acceleration? Same sign, opposite sign. So if I have positive velocity going up, I'm going to have negative acceleration going down. So my acceleration vectors are going to point in the opposite direction. So here's the deal with acceleration vectors. If they point in the same direction that you're going, guess what? You're going to speed up. If your acceleration vectors point in the opposite direction, guess what? You're going to slow down. That's it. So the beauty of this acceleration unit, and you keep this in mind, this is the acceleration unit. Every acceleration problem I only have, when I write any acceleration problem, it's a two-trick pony. I can either make it speed up and the velocity and acceleration have the same sign, or it's going to slow down and your velocity and acceleration have opposite signs. Okay, that's it. Those are the only two things that I can do. Every acceleration problem will only do one of two things. You'll either speed up and they have the same sign, or they're going to slow down and they have opposite signs. That's it. Those are the only two options I have for every acceleration problem. That's the first thing I have to decide when I write a problem. Do I want Zoe driving the carrot car to speed up, or do I want Zoe driving the carrot car to slow down? That's it. So start every question with that idea. Okay. So I got acceleration pointing down the hill. Now, when it gets to the top, what's my velocity going to be? 0. Now, on the way down, what happens to these velocity vectors? Hannah, first off, which direction are they going to point?
Down.
Down the hill. So going down the hill, you sit here and go, okay, well here's V1. So Hannah, going down the hill, are these velocity vectors going to get bigger, or are they going to get smaller? Bigger, because it's speeding up. So you draw these bigger going down the hill. So if you go back to what we said, oh, this thing's going to change direction, right? It has to do three things. It's got to slow down, stop, and speed back up. So your velocity vectors are going to get smaller. Then at the top, you won't have a velocity vector for a split second. And then your velocity vectors are going to get bigger going down the hill. Okay? That's it. So when I wrote this lab, with three things in mind. Because I want you to look at acceleration in three different ways. Mathematically, how it shows up on a velocity time graph, and how it shows up with vectors. Okay? So that was the whole point of this lab, to force you to look at acceleration vectors in three different ways. Now, here's the other thing. Going up the hill, everybody's cool. Oh, I have positive velocity, I have negative acceleration. Everybody's cool with that. That is not where the problem lies. The problem lies coming down the hill. Because you all want to harbor in the deep recesses of your mind the thought that, oh, going down the hill, it's speeding up, and you want to make acceleration positive. Okay? Don't do that. Okay? Do not make acceleration positive going down the hill. Why isn't acceleration positive going down the hill?
Because
Abby, what's the sign of my velocity going down the hill?
negative.
Are you speeding up?
Yes.
What do you know about velocity and acceleration?
They have to be the same sign to speed
They
up.
have to be the same sign. Because everybody wants to make acceleration positive going down the hill. Okay? Oh, you're speeding up, I should have positive acceleration. That's the other reason that I wrote this lab, is to smash that idea that positive acceleration means that you speed up. Okay, so we got that. So one of the things you're going to do is you're going to collect this data. So let's just make up some data. Let's say that going up the hill, my initial position was, I don't know, 0.10 meters. And my final position when it got up here was, say, 1.10 meters. Okay? So when I let go, the cart was at 10 centimeters, 0.1. And when it stops, it ends up here at 1.1. And let's say that the total time was 2.40 seconds. Okay? So let's say that's my total time, 2.4. So Kyle's going to time it from when it leaves to when it gets back, and we got 2.40 seconds. Now, what we can do, as long as this is symmetrical, okay, as long as we go up the same distance that we came back, what we can do is we can split the time in half. So that only works if it comes back to the same point. So like if I throw this ball up in the air and I catch it at the same point, I can say the time up is the same as my time down. But if I throw it and then let it fall all the way to the ground, I can't do that because my time isn't symmetrical. So this is going to be important. We can just assume that this is symmetrical. It's going to spend half the time going up and half the time coming back down. Now, you're going to draw two graphs. You're going to draw a position time graph and you're going to draw a velocity time graph. So let's talk about the position time graph. And I'm going to give you three different options for the position time graph. So this is going to be 1.20 seconds, and that's going to be 2.40 seconds. And we're going to end up out here at like 1.10 meters. So I'm going to give you three different options on this graph. Oh, that was horrible. Okay, there's curve A. There's B. And there's C. So those are your three options, A, B, and C, okay, for your position time graphs. So how many think A is going to be the correct curve? 1, 2, 3, 4, 5, 6. What about B? What about C? Okay, A is the right one. So why is A correct? Macy, why is A right?
Because it can't be this straight because it changes. The
Okay.
acceleration
It
changes.
can't be B, because what would B look like? B would be kind of cool to watch, because what would B look like? What's this mean?
Constant velocity.
Yeah, International Sign for Constant Velocity.
Yeah, that was like constant.
Yeah, so B would start off, you would give it a push and it would move up at a constant velocity, and then it would move back down at a constant velocity like that. Okay? Can't be B.
It's like it leaves.
It's like the.
Okay? What would C look like?
C would be it speeding up as it went up and then slowing down slowly as it went back.
Yeah, so C would be cool to watch.
It'd be like that.
Yeah.
From the top.
Yeah, so C, you would push it and it would start off slow and then it would go faster and then it would come back down and it would slow down before it got right back here.
It's like a railroad. Like a railroad
It'd
track.
be like if you had it at the bottom.
Kinda.
Like, cause whenever the train has to like slow down to stop, like that, then it has to like gradually speed up.
But it would be in reverse. Yeah. So A is right because that matches with what we observed. Okay, right? So now 1.20 seconds, you could draw a tangent line, and that tangent line would have a slope of 0 because that's when you are changing directions, right? Cool with this. All right. So we go from 0.1 up to 1.1, got this. So when you guys do this, you're just going to have to sketch this graph, okay? Because you don't know the exact points, but you know the general idea of what it's going to look like, okay? All right. Now, let's see how you all do on the velocity time graph. So on the velocity time graph, again, I'm going to give you three options. So this is your velocity time graph. So you have A, B, and C. Cobb.
DNA type stuff.
Huh?
Looks like DNA type stuff.
It does, actually.
Yeah.
Not really.
Yeah, kind of.
Okay, like.
The double
It's the
helix.
simplest of all.
Thank God for hydrogen bonds. Okay. So those are your three potential curves, A, B, and C. This is for the velocity time graph, right? We're not including the push. This is why they all start at some positive velocity. So, how many vote A? Okay. How many vote B? 1, 1. How many vote C? Okay. It's interesting. First block, it was an even split between all three. They literally, there was an even split between all three curves. So either Kyle, you're the only one that really sees it, or you're the only one that doesn't see it. So, now let's chit chat. What does the slope of a velocity time graph give you? Acceleration. F equals ma, right? So, for all of you that chose C, here's what you're telling me. Slope equals acceleration. So you're going to tell me that initially, what's ever causing this thing to speed up, or excuse me, to slow down, you have a big acceleration at the beginning because you have a steep climb. So you're saying the force is really, really strong at the beginning. And then the force becomes weaker because as it approaches its top, we're just going to slow down and stop. And then on the way down, gravity isn't as strong, okay? And then as it gets closer to the bottom, gravity gets stronger because the acceleration becomes a bigger value. Okay? That would be the physical ramifications of C. That the force of gravity is continuously changing. Now, do you think the force of gravity is a pretty constant force? Yeah, okay? Don't download the gravity forecast app. Okay? Oh, gravity is strong today. Gravity
Is that a thing?
weak today. Okay? Huh?
Is that a thing?
No.
But
It'd be the easiest app in the world to do.
Are those spots in the road that have like weaker gravity real?
Well, it's just because it's a function of how far you are from the center of the Earth. Like gravity at the top of Mount Everest is weaker than it is right here because you're further
Oh,
from
you
the
know how
center.
there's like random spots in the world where like stay on this, it's like different.
I can't imagine there's any real noticeable difference. There might be a thousandth of a difference, but that'd be about it. Okay, so look at F equals ma. Did the mass change? No. Did the force of gravity acting on the cart change? Nope. So the only one that's right is B.
Hey,
Now-
Kyle, you're so smart.
Now, I blame, and Mason's wearing this, I blame the Nike swoosh, okay? I blame the Nike swoosh. It's not the Nike straight line, it's the Nike swoosh. Because you all associate curved lines with speeding up and slowing down, okay? They don't call it the Nike horizontal line. It'd be boring, okay? Some marketing nightmare. So, here's what you have to remember about what acceleration is. Acceleration is not how fast you're going. It's the rate at which your velocity changes, okay? And so the only way you can change your acceleration is if you change the force. So B is right because gravity is what's providing that force. And gravity is a uniform force. So since force isn't changing, guess what? Mass isn't changing. It isn't like we drop an elephant on top of the cart halfway up the hill. Okay? Mass isn't changing, so therefore, guess what? Your acceleration isn't going to change. So, on this graph, you should have this action. Now, you're going to draw this graph, but you're going to flip out in the beginning. Because you're not going to know how fast it's going at the beginning. It's like, Perkamp, you expect us to draw a velocity time graph, and we don't know the initial velocity. You're right, we don't. Now, here's what I can't do. I can't take that displacement. And how are you going to calculate displacement knowing position final and position initial? P minus P naught. So that's going to be 1.10 meters minus 0.10 meters, and you're going to get 1 meter. So that's my displacement on the way up. Now, here's what I can't do. I can't take 1 meter and divide that by 1.2 seconds to get my velocity. Why not? Why can't I just take 1 meter and divide it by half the time?
It's not constant.
I'd be like the average.
Well, here's the
You're only
deal.
doing half the distance.
Well, here's the deal. What's the only time you can calculate velocity by taking distance and dividing it by time?
If it's constant.
If you have constant velocity. Does this car have constant velocity? No, it's a train wreck, okay? Can't do it. But I can calculate the displacement. Now, one of the things on this lab, everybody's data is going to be different. Your angle is going to be different. Your initial velocity is going to be different. Your displacements. On labs especially, I can only grade your process, okay? I can't grade your product. So I have to look at the work that you have done to get to this point. So one of the things when you get to the lab, I'm going to tell you at the top of the lab, in big bold letters, to show every calculation. So when you calculate displacement, this is what I expect to see. Oh, here's my displacement on the way up. I'm going to see final position minus my initial position. So now we have our displacement. And we have our velocity time graph. And you're going, but Mr. Burkamp, I don't know what my initial velocity is. You're right, I don't care what your initial velocity is. We'll find it, but I don't know what it is to start with. Now, let's play name that shape. So Allison, this looks like a triangle. So Allison, how do you calculate the area of a triangle? What'd you say? Divided by? Yeah, it's 1/2 base times height, okay? Now, let's chit chat. Katie Shearer, on a velocity time graph, what does that area represent?
Displacement.
Displacement. Oh, do you know what your displacement is?
Yeah.
Oh, that's kind of cool, right? So in this situation, we know that is 1 meter because I know how high I went up. It's kind of cool. Do you know what the base is? I know that's half the time, right? So I got that number. So I got the base. So what does the height of this triangle represent?
Velocity.
Oh, my initial velocity. That's like my y-intercept, okay, in a math class. Oh, right.
Whoa.
Whoa. Whoa. So, here's the deal. Here's when every problem that I work for you in this class, I'm going to follow the same 3 steps every time. Okay, this is going to be the 3 steps, and I'm going to show you this right now. The first thing I'm going to do is I'm going to write down the equation that I'm going to start with. Okay, area equals 1/2 base times height. That's what's going to get me to the dance. Okay. The next thing I'm going to do is I'm going to decide: do I need to solve this variable for a particular variable? Okay, excuse me. Do I need to solve the equation for a particular variable? So in this case, I need to get h by itself. Okay. So Mason, how can I get h by itself?
You have to divide.
I hate fractions.
Oh. Multiply.
By
2
and then divide by.
b.
Yeah. So 2a divided by my base is going to equal my height. Okay? That's what I got. So here's the deal. The reason that you do this is because you guys aren't, in an Algebra 1 class anymore. You're running with the big dogs. This is how science is done. Okay? You solve the equation first. The last step you do is you put in the numbers. Okay, because we're eventually going to be dealing with like really big numbers like the mass of the Earth and the radius of the Earth and all this other stuff. Okay, you don't want to have to write the mass of the Earth 5 times to solve an equation. Just put down an m, okay? The last thing you do is you put in the numbers. So, every problem I work, this is going to be the exact same way. Every problem I work in this class, you're going to see me write down the equation, then you're going to see me solve it, and then you're going to see me put in the numbers. If you look at my answer keys, that's the same process that I go through. Do you know why I do it that way every time? It works. Okay? It's the most efficient, best method to do it. I promise you we're not going to be halfway through this class and I'm going to change this up and go, oh, you can just do it in 1 step. Okay? I promise you from the beginning I will always show you the most efficient and best method to solve any problem. So literally, you're gonna see me work this the same way every time. Now, I'm gonna put in the numbers. So I'm gonna take 2 times 1 meter, and divide that by my base, which is 1.20 seconds. So somebody do me a favor, get a calculator, and take 2 and divide it by 1.2.
1.6 repeating.
So 1.67 meters per second. Okay?
It's awesome.
So that tells me that's the initial velocity of the cart. 1.67 meters per second. Got that number. Solid. Okay? Solid. Now, the only thing that's going to change with you guys are these numbers. Okay? Your height is going to be different. Your time is going to be different. But the process is going to be the same for everybody. So again, this is the only thing that I can grade is your process. Show me these numbers, show me the units. So, oh, I get velocity. Oh, that's meters per second. Okay, that way I know exactly what I've got. Now, the next thing I want to calculate is your acceleration. So, there's a whole bunch of different ways you can calculate acceleration. This is the simplest one. And we actually talked about this the very first day you all were in this class. And remember, acceleration is a rate function. It's the rate at which your velocity changes. And it's always going to be v minus v naught over time. So what we're going to do is we're going to look at this in 2 different paths. So on the way up, I'm going to start with some initial positive velocity, which we just found to be 1.67 meters per second. So I know how fast it's going, stay on the tracks, I know how fast it's going at the beginning. Now, when it reaches this point, what's my final velocity going to be?
0.
0. So I'm going to go from 0 minus 1.67 meters per second, okay, over time. And again, that's going to take that 1.20 seconds. It's going to take half my time, right? So, Macy, take negative 1.67 and divide that by 1.20 seconds.
Negative 1.4.
0?
Yeah.
Okay. So there's my acceleration. Okay? Does it make sense that that acceleration is a negative value?
Yes.
Because I went from a positive velocity to,
Negative.
what, to 0.
Oh, it's negative.
Okay? To 0. So I'm slowing down. My velocity is positive, therefore my acceleration has to be
Negative.
negative. Okay? So this is going to be one of the questions I'm going to ask you on the lab. I'm going to say, hey, on the way up, what's the sign of your acceleration? And do not give me this answer. Do not just say, oh, it's going to be negative acceleration because you're slowing down. Does negative acceleration always mean that you slow down? No. Could you speed up with negative acceleration?
Yeah.
If you had negative velocity. Okay? So negative acceleration does not necessarily mean that you're slowing down. Negative acceleration only means that you slow down if you have positive velocity. So keep that in mind. So stop that for a second while I hand out the lab. All right, so here's what you're going to need. So in terms of data, you're going to need the angle. If your phone doesn't have like an angle app on it, let me know. I'll bring my phone over and we're going to measure the angle. Okay? Put it on there, you just need the number. Then you're going to need the total time, start to finish. Have at least 2 people time it to make sure that your times are precise and pretty close together. Okay? If they're not, redo the trial. Then going up, you're going to need the initial position of the cart. Again, go off the front, the back, I don't care. So it's going to be where you let go of it and then up to here. Then on the way down, you're going to start here and you're going to end up back here. So we're going to look at like 2 distinct trials. Going from a positive velocity to 0, going from 0 back to a negative velocity. So up here, about a third of the way down, I tell you, include all numeric values in every calculation. So on this first part, I want to see your calculations of displacement. You don't have to show me that you took time and divided it by 2, okay? This is something that you're going to calculate. So I want to see the two calculations of displacement. This is going to be in centimeters. Change that into meters, divide by 100, you all can handle that. Then you got some questions to answer. Be very specific when you answer these. Now, when you get to number 7, here's what you're going to do on number 7. You're going to take a sheet of graph paper, and you're going to have something like this. So your position time graph is going to look something like this, okay? All right? Again, you just have to kind of freehand the shape because you're not going to know the exact position of the cart as it goes. Then, eventually you're going to draw a velocity time graph. It's going to look something like this. And again, initially you're going to know the time, you're going to know half the time, and then you're going to know this time. Just draw a line. When you find that velocity, that's what's going to go here. Then you can go back and write that in. So don't worry about the scale because you don't know how fast you're going. All I just want you to do is draw the line. Okay? Do not make this complicated. It is the simplest graph you will ever draw in this class. Okay? Do not make this complicated. Now, when you get over to page 2, the application of the integral triangle, this is where you're going to calculate the initial velocities and the acceleration going up, and the initial velocity, or excuse me, the final velocity and the acceleration going down. So, like for example, on number 16, this is what I expect to see. Something like this, okay? Where you're going to have, oh, here's the equation solved for the height, which is my initial velocity. 2 times whatever your displacement is, divided by half your time. Boom, there's your velocity. And then on number 17, you're going to calculate the acceleration. So number 17, that's how you're going to calculate the acceleration. So you can have a total of 4 main calculations to do. 2 that involve calculations of velocities, 2 that involve calculations of acceleration. So a total of 4. So this is what I want to see. I swear, if all you do is write down numbers and there's no units, I will have no patience for you whatsoever. This is about conveying information. This is not about writing down numbers. I know you all can write down numbers. That isn't the point. But do you understand what the numbers mean? Do you understand what you are finding? Okay? That's what I want you to convey. Now, when you get to question number 21, for now, just accept this equation that is negative 9.8 meters per second squared times the sine of the angle. So let's say that this angle, let's say we measured and it's 2.5 degrees. That's typically about where they fall. So what this is going to get you is a theoretical acceleration if the ramp was completely frictionless. Okay, so this is a theoretical acceleration. In about 2 weeks, you'll see where this equation comes from once we get into forces and inclined planes, okay? For now, just accept it. Eventually, you'll go, oh, that's where that came from, okay? For now, just accept it. So, there's an x in there. That just means times, okay? So, Macy, do us a favor. Take negative 9.8 times the sine of 2.5 degrees and make sure that your calculator is not in radian mode, okay? Make sure that it's in degree mode, or you're going to get completely jacked up values. So take negative 9.8 times the sine of 2.5.
It's negative 0.43.
Negative 0.43 meters per second squared. Okay? So that's my theoretical acceleration. That's what I should get under completely ideal conditions. Now, when you get to question 22, you want to calculate your experimental error. So when you calculate experimental error, that equation is over here on your Big Dog equation sheet under general information where it says this is like an absolute value. So, and these we're always going to calculate it the same way. So in number 22, you're going to take your theoretical minus your experimental divided by theoretical times 100. So in this situation, we got an acceleration of negative 1.4. We theoretically should have got negative 0.43. Okay? So what I'm going to do is I'm going to take that theoretical value, which is your answer to number 21. So I'm going to take negative 0.43 meters per second squared minus what I actually got, which was negative 1.14. And you have to watch the negative signs because there's a whole bunch of negative signs around on this. And then I'm going to divide that by negative 0.43 and then all of that times 100 because I want it as a percentage. So basically, you're going to take your answer to number 21, subtract your answer from number 19, and divide by your answer to number 21. So you take 21 minus 19 divided by 21, absolute value multiplied by 100. And usually these errors are pretty small. Usually they're around 5 to 10%. Okay, if you get an experimental error of like 80%, you have done something horribly, horribly, horribly wrong. Okay, horribly wrong. Okay, something went way south on this. Now, when you get to question number 23, so number 23, here's your setup. I've given you the ramp, here's the cart, okay? And the first thing you're going to do, this is going up the hill. So this is going to be V1, okay? Okay, that's going to be V1. So in the instructions I tell you, you're going to draw 3 velocity vectors, and you're going to draw 3 acceleration vectors. So this is going to be V1, it's pointing up the hill, right? It's pointing up the hill. So here's the deal. As it goes up the hill, one of 2 things is going to happen. Either your velocity vectors are going to be getting smaller, or your velocity vectors are going to be getting bigger, okay? That's what you have to decide. So if you think V2 is smaller, hey, draw V2 smaller. If you think V2 is bigger, draw V2 bigger. But I want to clearly see which direction that they're changing. If you think they're getting bigger, you draw them where I can clearly see them getting bigger. Then you're going to draw 3 acceleration vectors. Again, which direction? You have to decide which direction do you want the acceleration vectors to point, and do you want them to be the same size, or do you want them to get bigger, or do you want them to get smaller? If you want your acceleration vectors to be the same length, you draw them the same length, like exactly. If you think they're getting bigger, you draw them getting bigger. If they're getting smaller, you draw them getting smaller, okay? Then you're going to do the same thing on the way down. So on the way down, you're going to start with a V1, okay, pointing down the hill, oddly enough, because it's going down the hill, and then decide, oh, are going down the hill, are those velocity vectors getting bigger, or are they getting smaller? And then the same thing with your acceleration vectors. Which direction are they pointing? And are they getting bigger or are they getting smaller? Okay? Now, when you get to question number 25, here's the setup. We're going to take a ball and we're throw it up in the air. It's going to go to a height of 5 meters. This is going straight up in the air. At a height of 5 meters. To give you some perspective, this ceiling is about 2.5 meters tall. Okay? So it's going to go about twice as high as this ceiling. And we're going to start a stopwatch. We're going to shoot it off from the ground. It's going to go up. It's going to come back down. The total flight time is 2 seconds. So how long is this going to spend going up?
1 second.
1 second. It's going to spend 1 second coming
Down.
back down. You want to use the same techniques and the same equations on 25 and 26 as you just did before. If you're not sure how to do them, go back and look at this. Oh, it's going to look like a triangle. Oh, here's the area of a triangle. How am I going to find V naught? How am I going to find my acceleration? Okay, I'm done. There's about 10 of you, so maybe like 3 groups, something like that. Okay, I don't want 2 big groups of 5. And lab is due tomorrow. So if you're working on this and if you don't know if you're right or wrong, ask me and I will be more than willing to tell you. Right? So stop that.